Alright, so let's see an application of that vertical line test. When we're looking at algebraically, if something's a function or not, you're really looking at y. Is it just y, or is it something like y squared? That's how you know whether it's a function or not, is by looking at y. Again, with a picture, when you're looking at the graph, you're looking at, does it pass the vertical line test? A vertical line meaning if any vertical line touches the graph more than once, then it is not a function. If the vertical line touches the graph at most once, then it is a vertical function. So what I like to do here is come in with an actual vertical line, thinking about this if you just picture it. But think about as this vertical line goes from the left to the right. What I'm looking for is, does this vertical line touch the graph any more than once? Since at any point in time it only touched it at most once, we would say yes, this first one is a function. Okay, let's look at B here. I'm going to continue on with my vertical line. I'm taking my vertical line, and if you notice, at any point, we have a point where it touches more than once. For instance, here's a point where it touches both here and here. So there's a vertical line that touches it twice. If there's a vertical line that touches it more than once, then the answer is no, it is not a function. Continue on with the vertical line on the next one. And we can see that the vertical line touches at most once at any point in time. So yes, the next one, part C, would be a function. And then we look at the last one here. We take this vertical line through, and all you have to do is find any point. So for instance, here's a point right here, an x value, that if I look at that x value, it has two y values. It does not pass the vertical line test, so no, this is not a function. I also want you to take a quick look at the actual definitions of the functions. So what I'm looking at is on A, it's x plus y equals 1. Notice y is to the first power, so yes, this is a function. Look at B, y is to the second power, so no, we know that wouldn't be a function. The third one, y is to the first power, so yes, it is a function. And D, once again, y is to the second power, so we know it's not a function. So graphically, it's does it pass a vertical line test? Algebraically, are you looking at y or y squared? So the next thing we want to do is find the domains and ranges of the function. So if you remember on the previous page, we said the domain is the input, the range is the output. So the domain is the set of x values, and the range is the set of y values. Finding ranges of functions can be very difficult, but finding domains of functions hopefully isn't too bad. A domain of function is saying, what number can I put into the machine and get something out? Well, we naturally have some restrictions in some functions, if you remember. For instance, the square root of x. If you remember, you can only take the square root of non-negative numbers. In other words, 0 or positive numbers, not negative numbers. For instance, the square root of -4 does not exist. It is not a real number. So with square roots, you got to remember they have to be bigger than or equal to 0. And then another natural restriction that we have is with fractions. With fractions, you can't divide by 0, so the bottom can never be 0. So what you want to do is think of the real number line, every number from -infinity to infinity, and then think about what are my restrictions when you find the domain. We're always going to write our answers in interval notation. If the answer were all real numbers, if it was everything, for instance, y equals x squared, you can plug in any number, the answer would be -infinity to infinity. But let's look at these examples here to see what are our restrictions, or what are they. So it says the domain of a function is the set of x values that the function is defined. Graphically, we look at this as you go from left to right for which values of x is defined. Algebraically, we determine the function is undefined. Example, dividing by 0, square roots of negative numbers, etc. So example 7, determine the domain of the following functions and write your answers in interval notation. The function a, f of x equals the square root of x plus 2. So again, what do we need to remember with radicals? With radicals, we need to remember that whatever you take the square root of needs to be greater than or equal to 0. So whatever's underneath the radical, in this case x plus 2, has to be greater than or equal to 0. We subtract 2 from both sides. When we subtract 2 from both sides, we would have x is greater than or equal to -2. We would think about the real number line. Here's the number -2. Again, since x is on the left, the inequality points the direction we should shade. Greater than 2 is to the right of, greater than negative 2 is to the right of negative 2. We can equal that number, so we would use a bracket in that case, not a parentheses. Again, brackets, you include the number, parentheses, you don't. So the answer here would be bracket negative 2, comma, infinity, going always from left to right. So what we're saying the domain is to get a value out, you can plug in any number negative 2 or bigger. And we can plug in the number negative 2. Again, the square root of 0 is 0, so that's perfectly fine. Let's look at the next one here. Here's a nice fraction. If you remember with fractions, when you have fractions, whatever's in the denominator, doesn't matter, you do not simplify first. Whatever's in the denominator cannot equal 0. So in this case, we have x squared minus x cannot equal 0. Well, to solve that, there's multiple ways we can do it, but the best way of doing it would be to factor out an x. So if I factor out an x, this would factor into x times, well, x squared divided by x is x, and negative x divided by x is negative 1. So that factors into x times x minus 1. So in this case, we would set x, we would say that can't equal 0, and x minus 1 cannot equal 0. That gives me x can't equal 0. And then adding 1 to both sides, I'd have x cannot equal 1. So those are my two restrictions. If I plugged in a 0 or a 1, it would make the denominator of this function 0. And when the denominator is 0, the function's undefined. So it can't be the number 0, and it can't be the number 1, but it can be and should be anything else. So how would we write that in interval notation? Well, we start from the furthest left all the way to the right. So the furthest left would be negative infinity. Again, that has to be in parentheses. It would go to the number 0, and then we would use other parentheses. We could go from the next interval, don't forget the middle interval, which is the one most students forget, which is 0 to 1. And then we would go from 1 all the way to the right, which is all the way to infinity. So again, don't forget that middle one, and make sure that you're using parentheses here. We cannot include the number 0. We cannot include the number 1, because that would make the denominator 0. I always like drawing that real number line. It really helps how things look. I'm a visual learner, so if I can see it, I never miss that middle interval. So the next one says determine intervals of increasing and decreasing. It says a graph is increasing if, as you go from left to right, the function values or y values are increasing or going up. So as you go from left to right, it goes up. A graph is decreasing as you go from left to right, the function values are decreasing or going down. So mathematically, what does that look like? Well, here's the actual definition of this. Do I expect you to know the definition? No. But here's what, just to point it out, what the heck it means. So if it's saying x1 is to the left of x2, you can come down and you can look at this graph. That just means x1 is to the left of x2. When x1 is less than x2, it's less than. And so what we're saying is the y value for x1 has to be lower than the y value for x2. In other words, as I go from left to right, I'm going up. That means I am increasing. So that's an interval in which I would increase. If you noticed also from x2 to b in this picture, I'm still going up, so that's still increasing. I'm definitely increasing on that interval. So it seems to me on this entire interval from a to b, I'm actually increasing on this picture. So what does decreasing mean? It means the exact opposite. As you go from left to right, it's going down. So look at b and look at c in this case. B is to the left of c, and f of b, the y value, is higher than f of c, the y value. So that means it's going down. Because it's going down, this is decreasing. On the last interval here, we have increasing. So the concept of increasing and decreasing, extremely, extremely important to us. The reason that it's so important to us is this is what we find in calculus. Using calculus gives us the ability to find when is something increasing, when is something decreasing. And this is really, really important to us. Think of real-world examples. If you're a company and you're thinking about your profit, how much money you're making, you want your profit to increase. So you're looking for when would my profit be increasing? Calculus is going to give us that answer. Likewise, if I had costs, what would I want to do with my costs as a business? I'd be looking for when is my cost decreasing. So how could I decrease my costs? And it's really not your total cost, it would be your average cost, like your cost per unit, so to say. So how can I find when cost is decreasing? Well, calculus is going to give us that answer. So graphically, really easy. As you go from left to right, it goes up. As you go from left to right, it goes down. But calculus is going to give us the ability to figure this out algebraically. So that's just a preview as to what's to come and why we care about this, but let's answer this problem. It says determine the intervals of increasing. Well, we decided it was increasing from A to B. I'm always going to use parentheses here, and it's also increasing from C to D, we determined, and then we determined it was decreasing on the intervals B to C.